Okay, let's begin our lesson. So we talk about the growth rate of the thermal dioxide. Then we talk about the first stage. We mentioned the first stage is the linear region. So let's look at the first stage. So right now I draw the picture for the first stage. And first, before we form the first layer of the silicon dioxide, right now this is the silicon surface, right? Without silicon dioxide on the top of it, and then we have a lot of oxygen atom, right? We have a lot of oxygen atom here, we have a lot of oxygen, atom here. Okay, so today, for example, I have 10 oxygen here, okay? So today, for example, I already have so many oxygen atoms. I have 10 oxygen atoms, and I have the silicon surface. So the oxygen atom can react with silicon directly, okay? Directly. So this is the first stage. Within the oxide thickness of the 15 nanometer. So we say it's a linear region. It means the oxide thickness is the linear function of the oxidation time. Okay, the oxide thickness is the linear function. Here is the linear function of the oxidation time. And right now you see, although I have 10 oxygen atoms, right? And the oxygen atom can react with the silicon surface directly, right? So right now, do you think which factor can determine the oxidation? Which factor can determine the oxidation rate? Which factor? I mean, in this stage, I have a lot of oxygen atoms, right? I already have so many oxygen atoms, and I have the silicon wafer, silicon surface. So which factor can affect the growth rate or the oxidation rate for the first stage? I mean, right now I already have so many oxygen atoms, right? You don't need to consider about the oxygen atom is not enough. Right now I have a lot of oxygen atoms. So which factor will dominate the growth rate right now? I mean the first stage here. So which factor will dominate the oxidation rate right now and this moment? Right now you say we don't have the oxygen. We do have a lot of oxygen, and we do have the silicon. We already have the silicon wafer, and we do have a lot of oxygen atom. And which factor can increase the oxidation rate? Time. But the oxidation rate, yes, of course, if the time is longer, the thickness is higher, right? But however, maybe the slope is the same, right? I mean, I know the thickness will be thicker, yeah, but when we talk about the growth rate, yes, which factor is much more important? Yeah, I heard your answer. Your answer is right. You see, today if the temperature is 800 degrees Celsius, or maybe only 3 oxygen can react with silicon, right? And then when the temperature is a little bit higher, 9 degrees Celsius, right? I have more oxygen. That more oxygen can react with silicon, right? And then, if I further increase to 1000 degrees Celsius, it means all of the oxygen atom can react with the silicon, okay? So right now and first moment, I do have a lot of oxygen. I have a lot of oxygen, and I have the silicon. I have the silicon here. So right now, the temperature is the most important factor to affect the growth rate at the first stage. I mean, when the oxide thickness is smaller than 15 nanometers, just at the first moment. So the temperature is very important at the beginning of the oxidation. So we mentioned this mechanism, this mechanism, we call it reaction rate control. This is the first stage. We call it reaction rate control. Don't worry, we have the writing reaction rate control. If we go back to the previous page, we have the writing here, reaction rate control. Later we can go back to this page, you can see. And the first stage, reaction rate control. And what does that mean? What does that mean? Reaction rate control just means right now, at this moment, we have a lot of oxygen, but not every oxygen atom can react with silicon. So today, if I can further increase the temperature, if I further increase the temperature to 1000 degrees Celsius, it means all of the oxygen atom can react with the silicon surface. Then it will grow the silicon dioxide. So at the first stage, when the oxide thickness is within 15 nanometer, we mentioned it's the reaction rate control. Reaction rate control the growth rate, okay? Reaction between oxygen and the silicon. So reaction rate will control the growth rate and the first stage, okay? And the first stage, reaction rate between oxygen and the silicon can control the growth rate of the silicon dioxide for the first stage, okay? Right, it makes sense, right? And how about the second stage? For the second stage, for the second stage, right now when the oxide thickness is thicker, it means I have the third layer of the silicon dioxide. I have the second layer of the silicon dioxide. I already have first layer of the silicon dioxide. I have so many silicon dioxide layer on the top of the silicon. It's just like the block layer, right? Block layer, okay? So right now, I have the oxygen atom outside this silicon dioxide. So right now, I still have just for example, okay? So right now I have, although I still have 10 oxygen atom in the atmosphere or inside the chamber, I have 10 oxygen atom inside the chamber. However, all of these 10 oxygen atom will or cannot react with the silicon, right? Or because we have the block layer, we have 1, 2, 3, 3 layers of the silicon dioxide acting like a blocking layer. So the oxygen cannot come into contact with the silicon surface here, right? So today, all of this oxygen atom must diffuse. All of this oxygen atom must diffuse. Diffusion, okay? All of this oxygen atom must diffuse through the silicon dioxide, and then this oxygen atom can react with the silicon here, okay? Then we can grow the silicon dioxide, okay? So today, for the second stage, we call it parabolic region. It means for this moment, the diffusion rate control, control the growth rate, okay? Diffusion rate of the oxygen control the growth rate, okay? It makes sense, right? Diffusion rate of the oxygen, control the growth rate of the oxide, okay? So that's the reason the second stage, we call it parabolic region, and the growth rate is slower. Growth rate it's slower and becomes saturated, okay? Because when the blocking layer is thicker and thicker, you see, the oxygen must pass through the silicon dioxide, then it will come into contact with silicon surface here. So it takes some time. That's the reason the growth rate becomes slower. Okay? So for the second stage, we say the diffusion rate, or diffusion rate of the oxygen or the water through the oxide control the growth rate, of the oxidation. Okay, so for the second stage, you see, why do we write down the diffusion rate? Because we know the oxygen or water must diffuse through all of this oxide layer. Then the oxygen can react with the silicon surface, right? So it means when we talk about diffusion rate, it means we don't have enough oxygen, okay? We don't have enough oxygen. So the diffusion rate control, we don't have enough oxygen, okay? So diffusion rate control the growth rate, okay? We don't have enough oxygen because oxygen is here. Oxygen is not here, right? Oxygen is not near the silicon surface. Oxygen is outside the oxide, okay? So when we talk about diffusion rate control, you need the first thing in your mind is because we don't have enough oxygen, okay? Or we don't have enough oxygen. Oxygen is not enough, okay? Oxygen is not enough, okay? Or oxygen is not enough, or water is not enough. So that's the reason we say diffusion rate control, okay? So let's go back to the first stage. When we mention reaction rate control, why? Because at this moment, we have a lot of oxygen. We have a lot of oxygen for the first stage. We already have so many oxygen. So right now, reaction rate dominate the growth rate, okay? We already have so many oxygen. So if I can increase the thermal energy, like temperature, then all of this oxygen can react with silicon, okay? So the growth rate can be enhanced, okay? So for the first stage and the second stage, I think the simple way to think about the mechanism is for the first stage, you can think about the oxygen is enough, okay? And the second stage, we don't have enough oxygen, okay? We don't have enough oxygen. Therefore, diffusion rate control the growth rate of the oxidation, okay? So let's go back to see those two mechanisms, we will use for the deposition later, okay? So I hope you can understand and memorize the reaction rate and the diffusion rate control the growth rate, because later for the CVD, for the deposition, we have the same mechanism. Okay? So those two naming, the reaction rate control growth rate and the diffusion rate control the growth rate. Later, we will use the same mechanism for the CVD, for the deposition again, okay? Also, I prefer the first time you can try to understand. So the next time, it's much more easier for you, okay? We have some writing here. The rate of the oxidation growth has both a linear stage, the first stage, right? And the parabolic stage, the second stage, okay? We call it steel glue model, okay? The DG model or steel glue model, actually it's very complex. It's a very complex equation, okay? But we don't go through this equation. So if you are interested in the DG model, you can Google by yourself, okay? You can Google and try to understand all of this equation, okay? But here, I don't want to go through the detailed equation, okay? But you can Google if you are interested in the DG model, okay? The growth rate or the growth rate of the oxidation. You can Google by yourself. And the linear stage, or the first stage is the initial growth, or like up to 15 nanometer, and it consumes silicon on the wafer surface as a linear function of the time. This stage is the reaction rate control. Okay, so as we mentioned, because at the first stage we already have a lot of oxygen atoms. We have a lot of oxygen atoms. So today, if we can increase the temperature, then I can improve the reaction rate. So therefore, growth rate can be enhanced. Okay, so that's the reason we call it reaction rate control. Okay, for the second stage, parabolic stage, or for the second stage, because we don't have enough oxygen. Oxygen is outside the outside. We don't have enough outside. We don't have enough oxygen. So today, the diffusion rate of the oxygen control the growth rate. Okay? Or maybe you can write down by yourself. Okay? Diffusion rate of the oxygen or water control growth rate. Okay, it's much more easier to remember. Okay, right? Or easier to understand. Okay, the parabolic stage is the first stage. The linear stage is the first stage. The parabolic stage is the second stage. Okay. For the second stage, the diffusion rate. Which diffusion rate? The diffusion rate of oxygen and water can control the growth rate of the silicon dioxide. Okay. And the reaction rate between oxide and the silicon can control the growth rate. Okay. Does it easier for you to understand? Or the reaction rate between the oxygen and the silicon can control the growth rate of silicon dioxide. Okay, so you can write down something for you to understand. Okay, reaction rate between oxygen and silicon wafer can control the growth rate of the silicon dioxide. Okay, and the second stage, the diffusion rate of the oxygen for the dry oxidation, or diffusion rate of the water for the wet oxidation can control the growth rate of the silicon dioxide. Okay. Okay, so far so good. Oh, don't worry. The reaction rate and the diffusion rate control the growth rate. Or later we will talk about it. The same mechanism for the thin film deposition. Later we will mention it again. Okay. Okay. So let's move on to see the next chapter. For the oxidation, the most important application is for the STI and the locals. So I will tell you the difference between all of these process. Okay, the locals is the process, is the semiconductor processing we use with the technology know large than 0.25 micrometer. Okay, and STI is used. So when the technology know smaller than 0.18 micrometer. Until right now, we still use the shallow trench isolation. We still use. Okay, so do you still remember the shallow trench isolation between two transistors, right? The purpose for the STI and the locals are the same. In order to isolate between two transistors, so the location of the locals and the STI are the same, okay? So the purpose is the same. The location is also the same, okay? But with the different processing technology, okay? So I will show you locals and the STI. Of course, we use thermal oxidation for these two areas, okay? So for the locals, okay, before that, let me go back to this page first. I also can call this region for the locals because it's a local oxidation, right? Local oxidation we only have the oxidation in this area, in the central area, right? So it's a local oxidation, not a global oxidation, okay? So can you tell me what is the material? What is the material for this green area? Can you tell me? Today, if I want to put this silicon wafer, I want to put this silicon wafer into the furnace, You know, furnace is 1,000 degrees Celsius. So can you tell me which material I can use for this green area, which material I can use? Usually, if I want to generate a pattern, like I want to etch in this area, I want to imprint this area. Usually, this green area, I will use photoresist, right? Photoresist. But do you think it's possible to use the photoresist here? Can I use photoresist here, PR? Can I do that? Today, because I only want to have the oxide in the center region, right? So on the other two sides, I don't want the silicon dioxide, okay? So at first, I need to use the green material here to block oxidation, right? I don't want the oxidation happen here and here, okay? So that's the reason I need to use something to grow here and grow here, okay? And then I put this silicon wafer into furnace, okay? I input the oxygen atom only react with the silicon here, okay? So that's the reason only the central region we have the silicon dioxide, okay? We call it local oxidation, 局部的氧化 local oxidation, and only happen here because only here, only the central region, we have the silicon surface, right? So the local oxidation only happen in the central region, okay? Okay, so we back to our question. So today, if I want to put this material, this silicon wafer into the furnace, can I use the photoresist here? The answer is not, right? So the reason? Yes, very good. We mentioned in the furnace, the temperature is over or around 1,000 degrees Celsius, right? And what is the material for the photoresist? What is the material for the photoresist? It's it's a ceramic. No, it's not a ceramic material. It's not a metal material, right? It's the organic material, okay? 是有机的一种材料，有机的材料。It's photoresist is the organic material, okay? So it cannot sustain the high temperature, and of course, 1,000 degrees Celsius is impossible to sustain for such a high temperature. So usually, or not usually, so of course we cannot use the photoresist, okay? So which material we can use? Actually, we use silicon nitride because it's a very hot material, very strong material, okay? But do you still remember when we mentioned the silicon nitride? We know it's a very hot material with a high hardness, right? So today, a very hard material, can I put the silicon nitride on the top of the silicon directly? Can I do that? Silicon is soft. Compared to the silicon nitride, silicon is a softer material, and silicon nitride is a harder material. 硬度比较大. So today I put the silicon nitride. I cannot put the silicon nitride on the silicon directly. Okay, between those two materials, we need a buffer layer. Do you still remember which buffer layer we use? Which one? Like the lead oxide, screen oxide, right? Or whatever you call, it's the silicon dioxide, okay? So I just want to show you Today if I want to grow the silicon dioxide in the center, so on the right side, on the left hand side, I need to grow the silicon dioxide, and first very thin layer, and then I need to grow silicon nitride. Okay, the green silicon nitride just like a blocking layer. So on the top of the silicon nitride, later it will not have the silicon dioxide, okay? Because the oxygen atom can only react with the silicon surface, okay? So that's the reason only the central region we have the silicon dioxide, okay? So this is the principle for the local oxidation. Later we will use for our locals, okay? 这张图的原理刚好可以让我们等一下来介绍 locals local oxidation 的这个制成。你可以看到氧原子 oxygen 只跟 silicon wafer 产生反应，所以它只有 local oxidation， 只有局部会产生 oxide。局部是哪里？就是中间的地方才会长成灰色的 silicon dioxide， 旁边两边是绿色的 silicon nitride。silicon nitride 碰到 oxygen 不会再长出 oxide， 所以只有中间是 silicon wafer 的地方才会碰到 oxide， 才会长出灰色的 silicon dioxide。所以这个原理是我们等一下要用的局部氧化，就是 local oxidation 的原理。OK， so this is the principle for the local oxidation. We will use it right now. OK， so for the locals, let me see. The locals and the STI, they are the same location, the same purpose. The same purpose is to isolate two adjacent devices, isolate between two transistors, okay? Electrically isolate between two transistors, okay? And the whole name for the locals is the local oxidation of silicon, okay? Locals is the local oxidation of the silicon, okay? If you don't remember the whole name, it's okay. But at least you need to know the locals, okay? Because I believe more than 90% of the engineers in the IC fab, they know the locals, they know the function, the process, everything for the locals, but they don't know the whole name for the locals, okay? So likewise, I will not require you to remember the whole name, but the short name, you need to memorize it, okay? You need to memorize LOCOS, okay? Locals. You can write down the whole name, local oxidation of the silicon, or you want to write down LOCOS, okay? I think both are accurate, okay? So the locals is the traditional method because it has excessive literal growth, and it cannot be used for 0.25 micrometer technology and below. It means the drawback of the locals is the excessive literal growth. What does that mean? Later I will show you. So when the technology smaller than 0.25, then we use the STI to replace of the locals. Okay, so let me show you how the process for the locals, and it's very similar to the process of the STI. So later I will show you the difference between locals and the STI and the drawback for the locals. Okay, as we mentioned before, today we have the silicon wafer, and the first thing we need to grow pure oxide. We grow pure oxide, okay? And then we grow nitride, okay? So we grow first layer is the pure oxide in order to relieve the stress induced by nitride, okay? So we need to grow pure oxide before the nitride deposition, okay? In order to relieve the stress induced by nitride, okay? Nitride 直接长在 silicon 上面会产生一些残留应力或热应力，所以我们中间一定要长一层 oxide 薄的 oxide 去释放这个应力，避免一些缺陷在 silicon wafer 表面产生。So today the pure oxide must grow before the nitride deposition, okay? So right now the gray area is the nitride, okay? It's the nitride how we mentioned earlier, okay? And then how we go to photolithography department. So right now how we define the pattern, how we can define the pattern, and then how we define the pattern for the nitride, and we remove the central area, okay? We remove the central area, okay? So right now you see the gray region is the nitride, and the central area I remove the central area of the nitride. So it's the silicon surface, right? It's the silicon surface is exposed. The silicon wafer surface is exposed in the central region, okay? And then I put this silicon wafer into the furnace, okay? So I put the oxygen, and the oxygen only react with the silicon, okay? Oxygen only reacts with silicon. Oxygen will not react with nitride, okay? Oxygen will not react with nitride, okay? Oxygen cannot react with nitride. Oxygen only reacts with silicon. So only the central region, we can form, we can grow the silicon dioxide, okay? So the silicon dioxide right now is the yellow color. Can you see that? The oxygen only reacts with silicon. So only this square, region, this central square region, we can grow the silicon dioxide, okay? So that's the reason we call it local oxidation. Local means only this region, only the silicon region, we can grow silicon dioxide. So that's the reason we call local oxidation of silicon, locals, okay? So this is from the top view, okay? It's very clear, right? But right now, if I want to cut from this plane, so we can see the cross-section view. We can see the cross-section view here, okay? So you see if we cut from this plane, and you see the cross-section view is here. So here, this yellow region just means the yellow region here and the yellow region here, right? So those two yellow regions, we call it locals, okay? So just for example, if this is the first region, the second region, the first region is here, and the second region is here, okay? Because I right now we can see from the cross-section view, okay? So those two regions, we call it locals, okay? Do you still remember the other name for the locals? Do you still remember? We do have another name for the locals. We have another name for the locals. We go back to the previous slide. Can you see that? The field oxide, right? From the previous slide, we mentioned, and first we need to do the oxidation, because we want to generate the field oxide. So finally, field oxide is here, right? So here is another name, field oxide. Field oxide is equal to locals, okay? Someone say field oxide. Somebody say locals, okay? So field oxide, locals, they are the same, okay? But if my memory is accurate, in IC fab, I heard field oxide. I feel field oxide more often, okay? And locals I learned from textbook, but field oxide I learned from IC fab, okay? So I go back to our slide here. So for the locals, we also can call it field oxide. And for the field oxide, in industry, we prefer to write down FOX, okay? So I encourage you to memorize FOX by yourself, okay? Because in industry, sometimes we just write down FOX. F means field, R side means OX, okay? So next time when you see OX, you need to know it means the R side. OX just means the R side, okay? F means field R side. And the field R side just means the locals, just means those two regions, we want to isolate between two transistors, okay? And right now we still has the nitride here, right? And the nitride can protect the transistor. The transistor region here, we call it active region, 主动区 active region. Active region is the region where we have the transistor later, okay? So we need to have the nitride strip. You must know strip means remove. Okay? Strip, we use it so often in the IC fab. We usually say strip. It means remove, okay? Or in industry, we use strip. It means remove something. So nitride strip, it just means we want to remove nitride by the hot phosphorus AC, right? Do you still remember that? We use the chemical solution, we use the wet etching to remove the nitride. So we use the hot phosphorus AC H3PO4, and maybe this is the concentration and the temperature. I mean, the temperature is very high. Okay, but this parameter just for your reference. I don't need you to memorize very accurate temperature, but you need to know hot phosphorus AC just like over 150 degrees Celsius, or you can remember around 大概在150度C 左右对于这些参数，我们都知道大概的范围在哪里就好，你不用真的知道是160、160、170。为什么？因为参数我们每天在调，为了要让它的良率更好，这些参数所有参数都很重要，我们会撒一堆参数去调整它。所以你说，到底哪个条件最好？那你去看看其他的制程条件是什么。所以我们通常大概知道我们的范围在哪里。150到160、160到170，你知道那个范围在哪里？然后之后会有工程师去负责调所有的参数。他可能从150调到160，每间隔1度C。慢慢的调整，看哪一个蚀刻率最好，哪一个吃出来的 nitride 可以吃得最干净。我们有很多的工程师负责去调整这些非常细小的这个参数。所以在这参数的部分，你可以大概知道，它的温度1000度C 是什么？是 thermal oxidation 的温度。150度C 是要移掉 nitride 的温度，大概这个 sense 你要有。Okay, so I just want to remind you, this parameter just for your reference. Usually we have the sense like hot phosphoric acid is around 150 degrees Celsius. But usually we cannot memorize the accurate number because this number is changing all the time. So it's not necessary to memorize a very accurate parameter, okay? So right now, after I strip the nitride, so you see how the gray region is gone. So later I will remove the nitride. After I remove the nitride, I will fabricate the transistor here, right? After I remove the nitride, I will fabricate the transistor here, okay? Okay, this is the process for the locals, okay? But right now I want to look in, I want to look in this area, okay? I want to enlarge this area to tell you the drawback, the disadvantage of the locals, and the reason why don't we use the locals, okay? So right now, originally I have the cross-section view like this, right? So I look in, I enlarge this area, So today, you see, just like I mentioned earlier, so, thank you for our classmate to remind me. You see, originally, we have the nitride and the oxide, right? And the oxygen atom not only goes down to react with the silicon, oxygen will also go to the right side. oxygen will also go to, oxygen atom will not only go down to react with silicon, oxygen will go to the right side, okay? Oxygen will go to the left-hand side, okay? You see, oxygen will not only go down, oxygen will go to the right side because the right side here, we also have the silicon. Oxygen atom will go to the left-hand side. Here, we also have the silicon surface here, right? Okay, so today, if the oxygen go to the left side, what happened? What happened? You see, when the oxygen go to the left-hand side, it means when the oxygen go to the left-hand side, so it means here we also has the oxide growth here, okay, right? We also has the silicon dioxide formed here because the oxygen go to the left side and the oxygen reacts with the silicon here to form the silicon dioxide, okay? So that's the reason we say we have the lateral growth. We have the lateral growth. 我们侧向也会成长，侧边也会成长。Okay, so that's the reason why the first page we mentioned we have the lateral. We have the lateral growth. It means the oxygen will go to the right side or go to the left hand side. So we also have the lateral growth for the outside, okay? Oxygen not only go down, oxygen will go to the right side and the left-hand side, okay? So, likewise, today, we only assume the oxygen go to the left-hand side, or go to the left side. So, right now we have the lateral growth. Originally, the outside, we want the outside like here. So originally the gate length is here, right? Originally gate length is here. We want the transistor space is very large right now, okay? But however, when we have the lateral growth, right now, the gate length become here, right? Or the gate length become the green region, right? Because right now, due to the lateral growth, this region is the lateral growth, right? You see, the region between here and here. This region is the lateral growth. Originally, I only want the silicon dioxide stop here, but the oxygen go to the left-hand side to react with the silicon here. So all of this area is the lateral growth, okay? So the gate length originally is Lg. Right now it's become Lg prime, okay? So it means the locus will have a larger area. The locus has the larger area, okay? It will waste the area. It wastes the area of the chip because the area is very large due to the lateral growth, okay? And also, it has the effect of the channel encroachment. 有点像是把通道吃掉了、侵蚀掉了。Right, channel encroachment, because right now the channel becomes smaller from Lg to the Lg prime. So this area is just like this area is gone due to the lateral growth of the locus. Okay, and this region we call it burst peak. Okay, this region we call it burst peak. Do you know why? You can draw by yourself, okay? So if you have the eyebrow here, and here is like a bird's beak, right? 很像鸟的嘴巴, okay? So you can draw a cute picture by yourself, okay? So we call it a bird's beak, 鸟嘴, okay? So if somebody say the most disadvantage of the locals, we will say the bird's beak, okay? The bird's beak, it means the lateral growth of the locals, okay? Okay, we take 10 minutes for break.
you.